got another dynamics problem for homework 11's problem 2. And we have this young man. He is playing with a slingshot and he's shooting a 1 ounce, which is 1/6 of a pound, by the way, for us older folks. We remember what ounces were. For those who don't use SI, who use SI primarily, it's like, what's an ounce? Like 1/16 of a pound. The marble is shooting at a sloped concrete wall. The marble leaves the slingshot at 75 feet per second at an angle of 45 degrees. And he's holding it like 5 feet off the ground. And it hits the wall at a horizontal distance of B here of 100 feet away. And the coefficient of restitution is 0.6. And we're going to neglect friction, and we're going to try to figure out the distance that this thing lands away from the toe of the wall. We also want the efficiency of the collision, which just seems like, did I do that? I did that over in all 3 problems. Maybe I'm trying to emphasize something. I don't know. Maybe. Okay. So anyway, I've got it set up here. And so this starts out as a projectile motion problem. You can't get away from it. It's just inevitable. Let me see. Where's my cheat notes? There you go, cheat notes. Okay. So we're going to start off, and we want to figure out when it hits the wall. All right. Actually, that's sort of a giveaway. It's going to tell us. We're going to be able to figure out when it hits the wall, right? So if we have the initial velocity. Let me see. Let's break it into components. VA, I guess. Maybe I'm just gonna call it VA1 maybe. X is going to be our 775. I won't write symbols, just write down the numbers. 75 times the cosine of 45, as if it matters, right? And we're going to get the same thing regardless. So that's 53.03 feet per second. And VA1Y, it's going to be the same thing because it's 45 degrees. 53.03 feet per second. Okay. And, so in the x direction, it's kind of easy to do here, right? Which we could say, we know that it's a constant velocity process in the x direction. So xo, x naught plus the velocity a1 in the x direction times time, right? So we know that it's 100 feet starting, let's call that 0 right there, and plus 53.03, and now we could find the time. And so that time should come out to 1.886 seconds. So we know when it's going to hit. So if we know that, we can find the position. We can find out how high it hits. We could actually have done that just from geometry, can't we? No, not necessarily. We don't know where the toe starts, so we need to kind of know that. So let's get the y position onto this thing. And so that's going to be the y naught, that a right there, plus the velocity in the y direction times time minus 1/2 gt squared, right? So we're going to go 5 and then plus a 53.3, 03 times our 1.886 minus 1, and these are US units, so 32.2 and 1.886 squared. So we're going to end up with a y equal to 47.76 feet, say. Okay. We also might want to know the velocity. We do want to know the velocity at when it hits. So we'll call that 2, right? So we'll call that A2, and it's going to be the y velocity. And so that's going to be velocity a1 in the y direction minus g times t. And it's probably going to be going down, right? So we expect a negative number. So we'll start out with our 53.03 going up. Let's see. And we go minus 32.2 and our 1.886. And we're going to get a velocity of negative 7.684 feet per second. Okay, so it's time for the impulse momentum. Right now it hits the wall. It hits the wall going at a velocity. We can go velocity A2. I don't know why I'm calling it A. I guess the ball is A, maybe. It's going to have an x component of 53.03 feet per, not feet per second, dummy, I. That's what I meant to write. I plus our negative 7.684 J. And these are what, feet per second, right? Okay, great. Now let's take a moment and think about what this looks like for our impulse momentum. So we'll go initial, and we'll go impulse, and we're going to go final. So it's at a this steep angle thing right here. Let's draw this steep angle. Let's draw the ball. It's just a point mass, right? So it's just, let's see, here it is coming in, boom. Here it is right here, and then here it is right there, right? And I meant to, it's going to hit like this right here. And here it is coming in, right? So here's the normal direction, and of course here's the tangential direction, right? So the tangential direction is like there, the normal direction's right here. Same thing for right in there. We expect it to come in. So, and it's looking at the, we might not know the angle of the thing, but we know that it's going in with a a velocity that's going horizontal and then a little bit down, right? So, but we're not quite sure. So it's going to be something along the lines of like that right there, right? So, something along those lines. Well, maybe not now. We don't 100% know. We could calculate the angle, but one thing I do know for sure is that the normal direction. Let's see how did I decide to set this up? I decided to go the normal direction. I'm going to say is this direction right there. We'll call it EN. And the tangential, I've decided to make it this direction. Right, good. So this was the tangential direction. And these are based on that angle of 60 degrees, right? Yep. So it's right here is the angle. And just right there. So that's beta. Now, from an example we did in class, hopefully, we know that we can't use the conservation of momentum. Even though we've set this thing up, it's just sort of like a demonstration of what's going on right here. So we have a component in this direction, and I'm trying to think, yeah, I think we're going to go a component in that direction. I think that's how it's going to work out. We'll see here in a second, right? So this is, and we know that it's going to, let me see. Let me see. I want to see the actual values into this thing as I'm doing them in the tangential. Yeah, it actually has a tangential one. Okay, so it's going to have that same tangential velocity here, but we know it's going to come back this way, right there. And the sum of the total of these, if we do parallel lines right here, we're going to see that it's going to come up like that right there. Right? It's going to come up, back onto there. So let's see, I'll do the little trapezoids, make it look like coming in. So maybe I should label these. Here's the explosion part of it. I'm gonna have to switch pencils. I think I'm out of lead. Yeah, I think yeah, that's not good. I think I have another one of these though. Yeah, okay. There you go. I guess I'll label this as f d dt and integral f dt. This is going to be wasting time here. There you go. M A V A. Let's see. We got to be careful here. This is going to be 3, right? So this is going to be 2, and this is going to be 3 because this was 1 right there, right? So we got 2 is just before it's coming in right here. So we have M A V A 2. Oh, I'm at there. Damn it. Making a mess. There you go. And this guy is M A V A 2 normal, and that one is M A V A 3 normal. Now, I think it's going to be easier to get this, turn this into normal and tangential by creating a another coordinate transformation array, right? So I kind of started it up there, but I'll repeat it right here. Hopefully I'll do it right. I'll make it worth ET. Is that, yep. And here's EN. And here is our J. Here's I. All of a sudden I'm like really hungry. Here's beta. So we're going to go ET and EN. And here's our I, and here's our J. I didn't make these as neat as I could have. It's because I'm tired, I think. I didn't grade some stuff again. All right, so let's see. T is going to be cosine, positive cosine of beta. It's going to be sine of beta. And this is going to be negative right here. Yep, negative sine and positive cosine. And we know that beta is 60 degrees, right? Yeah. So let's get our VA2 and turn it into these coordinates. So I'll start out with the tangential coordinate. And so I take my I, and that's 53.03, and multiply it by my cosine of 60. And then I'm going to take my J, and it's a negative 7.684, and multiply it by my sine of 60. And then I'm going to take that same I and multiply it by my negative sine of 60, and take the negative 7.684 from here, multiply it by the cosine of 60, and these were feet per second, so that I get VA2 is equal to, whoop, I made a mistake, sorry. ET. This is EN. Let me see. Did I get that? I think I did something wrong there. One second, I'm sorry. Looking at my values here, I should have been two. Yeah, okay, so I'm good. I'm good right there, I think. Yeah, okay, I see what I did. So in the tangential direction, I have a negative 49.77 ET, and then in the normal direction, I should have 19.86. Is that right? Oh, I'm not feeling good about this. That should be a negative value. No, I got them backwards. That's why. So I wrote one before the other in the spreadsheet. That's why I did. I messed that thing up all the time. So this is 1986. 1986, right? And then this one should be the negative 49.77 EN. That's why you shouldn't try to make a video when you haven't write the whole thing out and then just write it down again. I don't know. And anyway, okay. So what we know is going to happen here is that we can't use the summation. We can't use this. We set up this diagram because we know it's true, but because this wall has infinite mass, we can't do an impulse momentum in the normal direction, even though we set it up. But that helps us it still helps us to try to know. We know that this thing is in the normal direction is going to come back and it's going to bounce. So we use the coefficient of restitution, but we recognize that the velocity before and after of the wall is 0, right? So maybe we'll call the wall B, right? The wall is B of the thing. So the velocity of A2 in the normal direction minus the velocity of B2 in the normal direction times E is going to be equal to the velocity of B3, oops, almost got it, in the normal direction, minus the velocity of A3 in the normal direction. But the wall ain't moving. So what you really have is the velocity here in the normal direction, which is negative 49, almost wrote 99, negative 49.77 times E, which you know is 0.6, is going to be equal to negative velocity A3 in the normal direction. So our conclusion is that velocity of A3 in the normal direction is going to be equal to 0.6 times that, but with it's going to flip sides, right? Well, that makes sense because it was going in that direction in the normal direction, which I called right there. Now it's going boom, but it's going less, right? By 0.6. I believe that, and it turns out to be 29.86 feet per second. Ready for a new page. Pumping out all of that good engineering paper. Boom. And so with 2 continued, dot, not 4 dots, because that means it's done, right? We're continuing at 3 dots. And we can write out now A3, right? So here, it's going to have the same tangential, right? So it's going to go 1986 ET t hasn't changed, but now it's 29.86 En. You know what we have to do, don't you? Coordinate transformation again. You can do this with like little angles and stuff, but man, I think people get really confused. I've seen students get really confused by that. So let's, we're going to take the VA3 and just take it again. 1986. Now this time it's ET, and we're going to go across with the cosine of 60 degrees, and then take 29.86 and takes times the sine. No. Here's the En, and we need I, right? We're trying to get the I's. So it's a negative sine of 60, and then it's an I. It's an I. Okay, doing it again. Take this. Now we're going to go down this column, right? So we're going to take the 1986, which I remember very well. It was a good year. I was 16, got my driver's license. Oh, what a great. I heard my phone. Nope, I don't think. All right, let's see. Plus 29.86 and times the cosine of 60. And this is J. Boom. Feet per second. Oh, sorry. Okay. So VA3 is going to be in the x direction. It's going to be negative. All right. So it is going that way. 15.93 I plus 32.13 J feet per second. Okay, great. So now we want to try to figure out where it's going to land. What we know right now is the kind of going up in that direction, right? Now we want to figure out where it's going to land. But we can know this height right here. I think we found this height. So we know the vertical direction. So we can figure out the time when it's going to land, and then we could figure out how far it went in the x direction. So that's our approach, right? That's our thought process as we're picking the thing apart. So when is it going to land? Well, it's going to land when y is equal to y original. Well, let me write these out with numbers, right? Let's say that it lands when y is at point 4, right? Because 3 is when it just leaves the wall. So let's say 4. So here's 4, and here's 3. It's the location of it when it's at 3 plus velocity of a3 in the y direction times time minus 1/2 acceleration of gravity times time. And we might want to say time, I don't know, call it time 3. Did I give it another name? I just call it time. All right, we already solved for time previously, but this is a different time. It's a different time. All right, so it lands when it equals 0. It starts when it has, it's at 47.76. It has an initial velocity in the y direction of 32.13. Time is a thing we need to find. And then 1/2, 32.2, and then t squared. So what do we got? Everybody's favorite thing to do, quadratic equation. So we could find that the time is going to be, I guess I'll do it this way. Negative 32.2, right, because that's b, so it's negative b, plus or minus the square root of 32.2 squared, 32.16. I'm sorry. Is that right? Yeah, it's 32.13. It's confusing. 13. Sorry about that. It's confusing because it's so close to being gravity, but it's not. And then it's going to be minus 4 times a, which is this 1/2 32.2. We know that's 16.2, but it's a negative 16.2. You'll see that negatives going to cancel each other out. And 4AC, right? So it's going to be times our 47.76. And if you're just totally confused by what I just did right there, it's all because you've been using the calculator to figure out the roots of stuff instead of doing a quadratic equation, but that's okay. Negative, well, I said negative, but then we go with 2a, where this is a right there. So it's going to be 2 times my negative 1/2 32.2, right? So that's going to be fine. Anyway, I go through this. I'm going to get 2 roots. I don't really care what the second root is. I can tell you what the second root is if you'd like. The second root, oh, no. I'm going to get it this way instead. I'll go this. Boom. Tell you what the second root is. I'll tell you what the second root is. The second root is going to be, boom. It's going to be 2 roots. A negative 0.9926 and 2.9884. Well, there's a lot more sig figs than we need, but and can't have negative time. Can't go back. Can't go back to 1986. But I remember it well. And okay, so now that we have that, we know the time. We can get the distance that it's traveling from here to there. Now remember, that's going to be this distance, so we're going to have to subtract out that, right? Because we were asked for that. What a jerk! I asked for it. But anyway, so we can get the distance. We'll call it delta x, 3 to 4. That's what I decided to call it. So I'm going to say that it's going to be the velocity if at 3 in the x direction. I guess it's a3, right? We said it a3. I don't know why I had to go with that a thing, but that's okay. a3 times time. So we said that that's going to be, where's that velocity? The velocity is here. Let's take the absolute value of the thing, right? So it's going to be, because we decided to go left. And it's going to be the 2.9886. What? Not 6, that's an S. And we decided that's 27.57 feet. But the distance, we have to remember that we have this distance right here. Well, we know this, and we know this angle. So this is if we take the tangent of this and multiply by that right there. No, we got to divide it. We got to divide it by tangent. Which way is it? Let me think. Let me see the x. Where did I get the x direction? Where did I get the x? There you go. No, see, I got this wrong. I wrote that wrong. I was looking at the wrong cell. Sorry. This is our 47.61. Yes. Okay. Boom. And then I'll say that the x at the bottom, let's just draw a little freaking triangle. That's what we'll do. Right? So you go this and this and this. And we want to find the bottom. I'm going to say I just said go x naught. I don't know. Let's call this y right there, right? So if I want to find x naught, I want to take y and divide it by the tangent of beta. Right, so all that's going to be is, what's that y, Josh? Well, they came out to be very similar numbers. So don't get confused by these numbers being very similar to the thing that we just did, right? They're nothing to do with each other. This was something we found early on with this. I hate it when that happens. Tangent of 60 degrees, and that's the number that I just wrote down a minute ago, 27.57 feet. So if we want D, we're going to find that it's going to be it's going to be that delta x 3 to 4 minus that x0. I don't know why I called it that. So it's 47.61 minus 27.57. And so our answer is a real boring 20.03 feet. Okay. Well, we also wanted, for some reason, I guess I really wanted to hammer this home, the efficiency idea. I want the efficiency of the whole thing. So you need the kinetic energy at the beginning and the kinetic energy at the end. So the kinetic energy at the very beginning was 1/2 mv A1 squared. Right, so that was really weird. Well, not really weird, but it's going to be really small little thing here because we're going to go 1/16 over 32.2. We could actually cancel this out, but let's go ahead and do it anyway. And the initial velocity was 75 feet per second. So I said, well, I didn't do it. All right, well, I got to do it by calculator. I got to do it by calculator. Well, there you go. 75 squared and 32.2 divided, multiply, divide by 2. Boom. We got a big old 5.459 foot-pounds of kinetic energy. And then take the kinetic energy at state 3. We never found what the velocity was up here, but we could take the velocity and we could do them by parts, but let's find what this is. Square root of 15.93 squared plus 32.13 squared. We're going to get a velocity 15.93 squared, 32.13 squared plus square root 35.86. Wow, that's interesting. Feet per second. So oh, damn. We're going to have to get the potential energy too at state 3. Yeah, we're going to have to do that. So we need the potential energy at state 3. We need the potential energy at state 1. I'm really regretting doing all of this. So potential energy at state 1 is going to be the weight of the thing times the height at 1, which is going to be 1/16 of a pound times 5. It's going to be very small. So 5 divided by 16, 0.3125 foot-pounds. So it might not matter much. The kinetic energy at state 3, right? This is after it has left the side of the wall. 1/2 mva3 squared, right? So it's going to be 1/2 1/16 over 32.2, and now we have 35.86 squared. But we have to remember it's up high, right? So we have to do the potential energy later. Let's flip that over there. We're going to square that, and we're going to go 1/16, boom, multiply 32.2, divide, 2, divide. All right, so it's got 1.248 foot-poundsies. And then we got potential energy 3, right? So that's going to be weight times H3, which is just Y3. I should write Y. Why am I doing this? All right, just go Y. This is the location of the thing. There you go, 3. There you go. And so that's going to have 1/16, and we know the Y location is, where'd you go? 47.76. So 47.76, 16 divide, you have 2.985 foot-pounds, right? So you get the total, the efficiency is going to be KE3 plus PE3 divided by KE1 plus PE1, or 1.248 plus 2.985 divided by 5.459 plus 0.3125. Makes me a little nervous. I sure as heck do not want to make energy. That's not a very good thing. Demonstration here goes 5.459. All right, so that ends up being 4.233 divided by 5.772, and yay, we did not make energy. We haven't. That's good. 5%. Okay. Let's write answers. And so part A is going to be D is equal to 20 feet. Well, I had a lot of work for that. And then B is going to be the efficiency is 73.4%. All right, and I did a simulation of this. But after this, I don't know how many people would actually be listening to this thing because it went on way too long. I've got to find a better, more efficient way to do all this. This is maybe just a bad idea all the way around, especially since it's almost 5:10 and we have class in about 10 minutes. But let's see. Let's take a look at the Solidworks simulation of the thing. And I made a Solidworks simulation. I even made a little target. I calculated ahead of time. This is where I think it's going to land. And this is where, this is what my equations say that it was going to land. And this is the little ball. I had to make it like 6 inches in diameter or something. Otherwise you couldn't see the ball. But I did assign it a mass. But it turns out the mass doesn't matter. This thing could be any size and it doesn't really matter. As the masses would cancel out almost everywhere. So we'll go to this motion study right here, and we'll go out to the end of the thing. So I gave it an initial velocity. You can't even see this. I hid this sketch where you could see where I assigned the initial velocity to the thing. But we can watch it go. Like, there he goes. Whee! You can see him. And he's about to hit the target. Boom! He nails right on that target. That's right up. That's the correct spot. I didn't fudge this at all. Whee! And I don't know what the hell that was. But see, it landed right on the target. Let's see. We can go back. Let's go. Let's pause it. Let's go back. Boom! Right there. How close did we get? They're not even showing us that frame. I don't know why not. Okay, and anyway, so we can continue and go boingy boing. I can make this a little faster. Boom. So I have the vectors turned on. Let's make this thing. Let's go. This is regular speed. Boom. You can see it coming up. I don't know why it's showing me that. Okay. It's got that little green thing happening. So what that is when I can play the results right to the let's go down to this. Go to the plot. I could show you the plot of the velocity. Oh, that's ugly. Let's fix this. No. Okay, this is the magnitude of the velocity, and you can kind of see that it kind of like drops like right here. That's after it hits the wall. So we could actually move this thing along, so it's like right around there, so you can kind of see as a line right there. You see that line? That line shows you this is the magnitude of the velocity right there, and this is in inches per second. So, but I checked it out, and it gets me right there onto the thing. But this is the time history of the velocity, as a magnitude, but it's like changing direction. So this is the absolute value. Like there's no zero velocity in here. I also had one in here where I had the y velocity. All right, so here's the vertical velocity only. So the other one was the combination of the total velocity which includes the extra. So I get the magnitude in that one. Right, and then but this one right here, it was just the vertical velocity, just the y component of it. But I turned on like the little vector thing in it, so like when it plays, it's not doing it. It's only, I think it only happens when I calculate it for some reason. It's got these things that has little bugs in it, but you can kind of like if you zoom in real quick, you could kind of see there. It's showing me the little green thing. But yeah, I got, it matches up to what we predict. It's a simple problem, really, but it's kind of surprising. One other thing it has to do that's really weak at is having the interaction between two bodies right there. That was the contact thing right here, and I made a separate one right here. Here's the initial contact one in between these two parts, between the ball and that's where I put the coefficient of restitution. So you could see that it would actually change. If you were to change this right here, you could change this to, let's make it a lot more. Let's go like 0.9 into the thing. And so you can see that it's going to go further, right? It should. Or I'm a liar. No, there you go. Yep, see, you can see how much further it went. Wow. So I'm going to come back and hit him. It shouldn't come back and hit him, right? Got really close. Got really close to peening himself right in the head. Ooh, it actually hit off this little post right there. That's interesting. Okay, that's enough. I got to get ready for class, unfortunately. I use so much time to make these videos. I don't know if it's worth it. Here, 40 minutes.